Let's go ahead and finish off 11.4, proportional partitions. We have our last theorem in lesson 4 here. It's theorem 11.4.3, the triangle angle bisector theorem. The bisector of an angle in a triangle divides the opposite side into segments that are proportional to their adjacent side lengths. So, taking a look at this triangle, we have a line AD that bisects this angle BAC. You now end up with two congruent angles. And when you have the situation where you see the two congruent angles with a line drawn to the opposite side, this theorem will apply. And besides the fact that AD bisects angle BAC, we can now do proportions with this triangle to solve for parts. So the proportion would actually be BD to CD. So the two parts of the base of the triangle in proportion to each other, and then the sides, AB and AC. So the sides will line up in the same order that the pieces of the base lined up. You'll have BD on the top and AB on the top of your proportion. You will not have BD and AC. So be sure you line up that proportion correctly. In example 4, we're going to use this theorem, and we have a triangle ACB. We can see that there is a bisector here. The bisector is CD. This just happens to be a 90-degree triangle, but it works with any triangle where the angle is bisected. This bisector forms segment BD and segment AD, also known as X and Y. So we want to begin by using the P theorem, because this is a right triangle, to solve for AB, which will be this total length. And it will be AB squared equals 3 squared, which is the side of the triangle, plus 4 squared. So this is your usual P theorem formula. And we end up with AB equals the square root of 25, which is 5 inches. So this whole piece right here, AB, equals 5. And let's fill that in there. Now we can go ahead and begin solving for variables. Let's begin with setting an equation to y. And we have x plus y equals 5, because we now have the value of 5. And if we turn this equation around to equal y, it will be y equals 5 minus x. So let's go ahead and add the 5 minus x to our drawing. And 5 minus x will go into this piece. I'll move this 5 over. Remember, it's the overall length. So we have what y equals. Now we can use our proportion. And our proportion is, once again, the one portion of the base of the triangle over the other portion. And then the side to the other side. So we have x is to 3 as what was y, it's now 5 minus x, is to 4 inches. So here's our proportion. And why are we not using y? Well, if we use 5 minus x, we now have only one variable in this proportion. If we had two variables, we would not be able to solve it. So if we multiply across, we'll have 4x equals 15 minus 3x, which equals 7x equals 15. If we divide both sides by 7, we have 2 1/7 inches. So x will equal 2 1/7. And we'll go ahead and place this over here. And now we can go ahead and finish solving for y, because we left it not complete. And we can substitute the x into here, which is 2 1/7, and we now have 5 minus 2 1/7, which is 2 6/7. So now y becomes 2 6/7. So this was kind of a difficult example, but the basic steps that you want to use, first and foremost, make sure you know which theorem you're going to be using for which figure. Then I suggest making a proportion just like they have in the theorem. So if it says AB over BD equals BC over AC, mark that down and then fill in your known values in your proportion. And if you don't have 3 known values, you have to figure out a way to solve one of those sides. And in this instance, we didn't have 3 values. We only had 2, the 3 inches and the 4 inches. So we had to set y to in terms of x so that we could solve. So let's take a look at an example. We have a similar situation. You can tell it's similar because we have a bisected angle here. So let's set our proportion, and our proportion will be x to x plus 10. So x to x plus 10 equals 30 to 40, or 30 divided by 40, or 30 over 42, sorry, I'm saying 40, it's 42, and which I'm going to reduce right away to 5/7. So it's x over x plus 10 equals 5/7. I will go ahead and multiply across. 7 times x, 7x. 5x plus 10 is right here. We go ahead and simplify, and 7x equals 5x plus 50. Subtract 5x from both sides. You have 2x minus 50, and x will equal 25. We're not done though. We have to find the value of x plus 10, and that would be 25 plus 10, which is 35. Here's another example. This one uses the corollary to the side splitter theorem. This is where you have the parallel lines and transversals. This one is actually a closed figure. In your book for the theorem, they used an open figure, but that's fine. And the proportion that we had was, on the left side, one piece to another piece, and on the right side, in the same corresponding order, one piece to another piece. So we'll take the upper pieces here to begin, and we'll set it R is to S equals T is to U. They ask us to solve for U, and they tell us that R is 2, S is 5, and T is 13. So I wrote the original proportion and substituted the numerical values. We have 2 over 5 equals 13 over u. If we multiply across, we have 2 times u is 2u. 5 times 13 is 65. And if 2u equals 65, we can divide 65 divided by 2, and u will equal 32.5. Here is another with the triangle angle bisector theorem. It asks us to find AB, CD, and BD. So you can tell this one is a little bit different. We actually have more than one term. On one side, you just need to remember how to use your distributive property. And we're going to go ahead and in this one, they actually set, because it's the triangle angle bisector theorem. In the other theorems, we used AC over BA, which would actually be 10x over 15x, and then we used 12 over x plus 15. However, I noted in the examples I was given that they went ahead and compared the figures differently, the values differently. So in this one, they compared the two sides to each other and then the two base pieces to each other. But I can tell you that I worked out the problem and they end up exactly the same. So I believe they use this example to show you that you can move these proportions together as long as they're, you can move these proportions around as long as they're corresponding, because the old theorem would have had 10x over 15x, and it would have had 12 over x plus 15, but when I worked it out, we still had 180x equals 10x squared plus 150x. So it worked out the same. If we combine like items, subtracting 150 from both sides, we have 30x equals 10x squared. If we divide both sides by 10, we have 3x equals x squared. And if we divide both sides by x, we end up with, and I reversed the order, so don't let that confuse you, x equals 3. So we can now solve for our pieces, and 3 plus 15 is 18. 15 times 3 is 45, and 10 times 3 is 30. So I know that you can mix these proportions up, but until you get really comfortable with them, I would use the theorem proportion that they showed you and do your problems that way. And the last one is example, additional example 4. We have the side splitter theorem, and it says find BE, which is this piece right here, if EC equals BD, BD, and they are both a length of 6, and DA equals 9. So I will set up my proportion, BD over DA, BE over EC. I'll fill in the known values, and we end up with 6 over 9 equals BE over 6. You can see this is a geometric mean, so we'll end up with a squared number here, and 9 times BE is 9BE equals 6 squared, which is 36. So if we divide both sides by 9, BE equals 36 divided by 9, which equals 4. So that was fairly simple. Just make sure you're setting up your proportion in the right order. Your homework is number 6, 10, 12 through 14, 19, 22, and 23, and numbers 27. The homework problems that are in the 20s are a little bit more difficult than the other ones. If you need some assistance, be sure to contact me, and we'll work those problems out.